Okay, so last time we did a bunch of examples of applying Hund's rules to get the spectroscopic term notation for different electron configurations of atoms. And you'll get to do more of that for homework. But now that we've used it, let's give a little bit of a defense of Hund's rules. And this is sort of hand wavy and not rigorous at all. Okay, and the real reason why we believe Hund's rules is simply the fact that they work, that we've noticed that in many examples they work. But we can give sort of hand wavy explanations for them. So for rule one said that the larger the spin was, the total spin was going to be the ground state. And so the reason for that is if you have larger s, then that means the spin wave functions are more symmetric. And that's just because we know when we add two angular momenta together, when the total angular momentum is maximal, that's a symmetric combination. So if the spin wave function is more symmetric, that means that the spatial wave function has to be antisymmetric. I'm going to write more antisymmetric here, because in some cases you can have mixed symmetries and antisymmetries between these. And that means the electrons are farther apart. Okay, and the fact that the electrons are farther apart means there's less repulsion, and so less repulsive positive energy, which means there's a lower energy. And so they are more bound. Okay, so it might bear a little bit of explanation why we say that the electrons are farther apart. The reason for that we can sort of break down like this. If your spatial wave function is antisymmetric, that means the wave function vanishes when the electrons are on top of each other. So it vanishes when, for example, R1 for one of the electrons is equal to R2 for a different electron. Okay, but the wave functions tend to be continuous functions. And so if they vanish when the coordinates are equal, then that means they're going to be small when the coordinates are almost equal. So by continuity, they're small. The wave functions are small when R1 and R2 are close together. Okay, and then the rest of the argument is then you get less repulsive energy, and so a lower energy means the state's more bound. Okay, that was rule one, and then there's rule two. Rule two says you tend to lower the energy if you have a larger L. And so one way of thinking about that is your spatial wave function is more spread out. Okay, and that means the electrons are again farther apart. Okay, and then the rest of it is the same discussion as for the previous rule. So another way you can think about this is suppose we're looking at we're going to do a very classical picture of our electrons orbiting around the nucleus, which of course is completely wrong, but it's sort of, you can think of this as more of a mnemonic rather than a real physics argument. But suppose I have two electrons and they're orbiting around, and let's say they're orbiting around in the same direction around my nucleus. Okay, and so we would describe that situation by saying, if the z direction is out of the page, then we would say that they have the same z component of angular momentum, and then when you combine that to get the magnetic quantum number, the m sub l, it's going to be the addition of the two individual electron m sub l's. Okay, now in that situation, the electrons can stay far apart from each other because as they're orbiting around, they just stay on opposite sides. Okay, and so the electrons don't meet. This is a very anti-quantum point of view. But then conversely, if we think of it like this, here's my electron and here's my other electron, and now let's say they're going opposite directions, then m sub l would be ml1 minus ml2. Actually, I shouldn't put the absolute value, perhaps. Okay, because they're going in opposite directions. But now the electrons do meet. They can't stay on opposite sides. And so when they're going to be closer together, and therefore they will repel. Okay, and that repulsive energy is a positive energy, which will add to the energy of the state and make it less bound. Okay, so that's hand-waving justification of rule 2. And then there was rule 3. So to understand rule 3, we want to understand the perturbation that comes from the spin-orbit interaction. And so just schematically, it looks something like this. It's something that depends on L and S times L dot S. Okay, and without even worrying about what the something is, if we just look at the L dot S part, we use our standard trick. So now I'm going to be writing J times J plus 1. So when I write this, now I'm taking these to be the quantum numbers that go into the term notation. Okay, and so right away, without even knowing anything else, we know that the thing that will extremize this energy and make it as small as possible will either be the largest J possible or the smallest J possible for a fixed L and S, which is what Hund's rule 3 talks about. Okay, so this is lowest for extreme J. And now's where you need to know something about L and S. It turns out this f of ls happens to be positive for less than or equal to half filled. Okay, and so then when you extremize it, you're going to pick the smallest possible J, and it happens to be negative in the opposite case. Okay, so a question that arises because this is just an approximation is the following. Is what's the lowest z for which this fails? Or is there any case where it fails? We expect that when we go to larger z, it will not work as well because the spin orbit gets more and more important and less reasonable to treat it as a perturbation. So what is the lowest example for which Hund's rules predict the wrong thing? So predict the wrong 2s plus 1 Lj ground state. And I looked around and I was unable to find an example of this, either working on my own or in the literature. So if you find an example like that, please let me know. I did do quite a bit of trying to find one though, so I don't think it's too easy, but that will be worth a bounty of 2 points as correction to the lecture notes if you can give the lowest or any example in which Hund's rules actually fail to predict the right ground state. Now, there is a big difference between predicting the right ground state and quantitatively getting the properties of the ground state and the other states correct. And so it is well known that the Russell-Saunders coupling scheme, even though it may predict which one of them is the right ground state, it doesn't get the properties very well when you go to larger Z. By properties, I mean the details like energy splittings and even things like transition rates when you take into account electromagnetic transitions between different states. So there's an alternative scheme, alternative to Russell-Saunders, which is often used for larger Z, larger atomic number. And this is called the JJ coupling scheme. It might be called the JJJ coupling scheme or the JJJJJ coupling scheme, but I think it's called that because the classic examples where it works nicely are examples where you have two electrons in the two unpaired electrons. Okay, so the idea, so this is for larger Z, this is better than Russell-Saunders or LS for predicting things like energy splittings. And the idea is the following. Since we know from doing a homework that the effects of the spin orbit interaction, which I remind you are proportional to a sum over the electrons, some radial factor function that we won't worry about too much, and then an Li dot Si for the individual electrons, that scales like z to the fourth. Its effects scale like z to the fourth. So instead of treating it as a perturbation, we'll treat it as the main effect. And then eventually for large Z, we'll treat the electrostatic things as the perturbation. Okay, so we treat the spin orbit as large and the rest of the perturbation, which we call W, as the perturbation to that, the smallest part of the perturbation. Okay, so what does that mean? That means we should look for states in which this operator or these operators Li dot Si are diagonal. And so we're going to use our standard trick to write it like this. Okay, so now on the individual combinations of orbital and spin angular momentum, I'm doing the trick of how we write the dot product of angular momenta. These are individual quantum numbers, individual electron quantum numbers. Okay, and of course this one is 3/4 for each electron. And the L sub i's here you're going to get by looking at the electron configuration. A 2p would mean the L would be 1. 3s would mean the L would be 0, etc. Okay, and so now the coupling scheme approximation is we first combine the individual spins with the individual orbital angular momenta to get individual total angular momenta. And then we combine those to get the total angular momentum. Okay, and so instead of writing 2s plus 1 Lj, For our term symbols will look like the following. Term symbol just means the code for how the angular momenta states look. And so we have J1, J2, up to J sub n. And then we write a capital J to tell us how those combine to give the total angular momentum of the whole thing. And these states will have degeneracy 2J plus 1. And that's just because M sub capital J will run from negative J up to J in integer steps. Okay, so their classic example of this is lead. Nice large Z, nice large atomic number. So lead has atomic number 82. And so if you fill out your electron configuration, you find out it's the same as xenon. And then you put a bunch of electrons in the 4f. And the number you can fit in a 4f is 14. And the next thing is 5d, and you can fit 10 in there. And then the next thing is 6s, and you can fit 2 in there. And then what's left over is the 6p with 2 electrons in it. So that's the incomplete shell. Is 6p2. And so if we count states, ignoring all the complete shells, because there's only one way to put electrons, pack them into a complete shell. So the incomplete shell has 6 times 5 over 2 times 1. We're counting the anti-symmetric combinations. And that's 15 states. And if that's familiar, it's because this is exactly what carbon looked like, except for carbon, instead of 6p2, it was 2p2. So everything else, if we did Russell-Saunders, everything else would be exactly the same as carbon. So according to Russell-Saunders, or LS, with Hund's rules, it's just like carbon. Okay, and the ground state term will be 3p0, which is what we found for carbon. All right, but now let's look at what the JJ coupling scheme says. So according to the JJ scheme, okay, each J, each little j, of which there are 2 of them, can be either 1/2 or 3/2. Okay, and the reason for that is just that we're taking angular momentum 1, combining it with angular momentum 1/2. The 1/2 is the spin. The 1 is because we're in a p shell, or a p wave state, because it's 6p. Okay, and that, when you add 1 and 1/2, you get 1/2 and 3/2 as the possibilities. Okay, so each of the 2 J's can be 1/2 or 3/2. And so now we can figure out what are the possible capital J's. The possible capital J's are, so what if we have 1/2 and 1/2? That can be a 0, which is anti-symmetric, and a 1, which is symmetric. The other thing we could do is we could have a 3/2 and a 3/2. And that could be this. Okay, and so this anti-symmetric combination will work, this anti-symmetric combination will work, this anti-symmetric combination will work. But we could also have one of the electrons be in the 1/2 and the other one be in the 3/2 of the individual J's. So these are, in the left, these are the J's. Okay, and when I add those together, I get angular momentum 1 and angular momentum 2. And when I'm adding two non-identical angular momenta, I can't give those symmetry or anti-symmetry labels. But the thing is, there are two of them because I can do 1/2 and 3/2, or I can do 3/2 and 1/2. So when I get 1 plus 2, I can take linear combinations of those and make one of them symmetric and the other one anti-symmetric. So the moral of the story is, at the end of the day, what are the anti-symmetric combinations I can make? Okay, I can have J be 0 from this one, or 0 from this one. Okay, and that counts separately because it's a different state. Or it can be 2 from here. Okay, or it can be either one of those two because I can make one anti-symmetric and one symmetric combination out of each one of them. So I'm going to get 1 and 2. So those are all the possible J's we can have. And let's count up the total of them, the total degeneracy. So the total degeneracy for a given capital J is 2J plus 1. So for the J equals 0, it's 1. And for the other J equals 0, it's 1. And for the J equals 2, it's 5. And for the J equals 1, it's 3. And for the last J equals 2, it's also 5. And when I add those up, I get 15, which is what we predicted and knew that we should get for the total number of electron states that you can have. Okay, and you can write out what they are now in JJ coupling term notation. So let's write it like this: J1, J2, subscript J can be 1/2, 1/2, 0, 1/2, 3/2, 1. I'm writing them in an order that happens to correspond to their increasing energies experimentally. Okay, and then there's 3/2, 3/2, 2, and 3/2, 3/2, 0. Okay, and this one right here is the ground state, the 1/2, 1/2, 0. If you look at things like transitions between these states and the energy splittings and the fine structure of these states, and the hyperfine structure, which we haven't talked about at all for these, you find out that they are very well described by the JJ terms and not very well described by the Russell-Saunders terms. However, it actually happens that the Russell-Saunders term at least gets the ground state right. Okay, so both the Russell-Saunders and JJ schemes agree that J equals 0 for the ground state. In other words, if you apply Hund's rules, if you just, well, you enumerate what you get from Hund's rules and apply Hund's rules, they agree on that much. Okay, and so just as a reminder, that's what we set up here. That was our Russell-Saunders prediction, just stolen from what we did for carbon, and indeed J was 0. Okay, and so it's what happens in the real world is that for medium large Z, the truth is somewhere in between the two extremes. So somewhere between Russell-Saunders and JJ schemes. That being the case, usually when you find a periodic table of the elements that bothers to give you the spectroscopic notation, they almost always give you the Russell-Saunders or the LS scheme spectroscopic notation, even for states where it's known that it doesn't work, it doesn't describe the state perfectly well. they'll still give you that because it usually gets the angular momentum right, even if it doesn't get other details of the state correct. All right, any questions on that? Because we're about to do a significant change in topic. All right, so our next big topic is going to be approximation schemes for time-dependent problems, or approximations for time dependence. And I'm actually going to be doing things a little bit out of order from what's in the notes, just for variety. Not for any particularly good reason, but just because I feel like it and because we can. So I'm going to start with a relatively simple case. And then when we do this simple case, we will get a result. And then we will later redo it with more powerful methods based on time-dependent perturbation theory. And we will check that we get the same answer. So this relatively simple thing is going to be called the sudden approximation. And so when you hear sudden approximation, that's what happens when you are suddenly changing the Hamiltonian. And so we suppose that we're going to be dealing with a Hamiltonian which has the following form as a function of time. So at early times, it's just going to be some simple constant sort of thing that we're going to call h0. So that's what it's going to be for time t less than 0. And then it's going to do something complicated. So I'm going to call that h int. Let me just call it I in lecture so that I don't have to write nt all the time. So I'm just going to call it h sub I. And it does something complicated, but it only does it for a short time. So this is going to be for 0 less than t less than some short time delta. And then it's going to go back to be something simple again, but maybe not the same simple thing it started out as. So I'm going to call that h0 prime 4 times larger than delta. So what do I mean by simple? What I really mean by simple in practice is I mean that I know the eigenvalues and eigenstates of h0 and h0 prime. Also that they're constant. So h0 is some constant Hamiltonian. In other words, it doesn't have any weird time dependence built into it. And I assume that it has eigenvectors that we're going to call n with corresponding eigenvalues that I'm going to call curly e sub n. Okay, and same for h0 prime, except it's not. When I say constant, I don't mean constant as in just a number. What I mean is it doesn't have a time dependence built into it, like say a cosine of time built into it. So this has eigenvectors that I'm going to call m prime with corresponding eigenvalues curly e sub m prime. And so the good thing about that is that means for early times and late times, we know how the state evolves. Okay, and so let's write that down. We know that because we know how stationary states evolve and we know what the stationary states are. So for t less than 0, the state as a function of time has to be some linear combination of the energy eigenstates. So I'll write a sum over n, some coefficients that we don't know, let's say, the energy eigenstate, and then each energy eigenstate evolves in time like the exponential of its energy times time over h bar. Okay, and then for time t greater than delta, we also know that it's not complicated, or not as complicated as it could be. Now we're going to sum over m prime.
Was that first one negative or smaller than delta?
Which one?
The top one? T smaller than 0 or is that delta?
No, t less than 0,
Okay, and the
right?
second
So
one is
we have for times less than 0, 0
okay.
is when interesting things start to happen. For t less than 0, it's h0. And then something weird happens for some short period of time. And then for time t greater than delta is when it's h0 prime.
Okay, thank you.
So for the moment, we're not going to talk about what happens in the middle. We're only going to talk about what happens on either side. Okay, so psi of t is sum over m prime, some coefficient, b of m prime, times the stationary state. And then we know each stationary state just gets a phase multiplying it, which looks like the following. Okay, and I'm going to put a t minus delta here, which I'm free to do because the minus delta part is just a constant. It's actually a phase. And so whatever that is, I can absorb it into the definition of my couplings out front. And I haven't said what those are yet anyway, so I might as well just, I can absorb anything I want into those as long as it's a constant. Okay, now we have to worry about what happens in the middle. And so we're going to look at Schrodinger's equation for that. So Schrodinger's equation tells us how the state evolves. Okay, and the Hamiltonian is now a function of time, meaning it depends explicitly on time. Okay, and so we're going to imagine integrating this though. So if we integrate both sides, then on the left side, it's nice because then we can apply the fundamental theorem of calculus. If we do this, okay, that's going to be just I h bar the state at time delta minus the state at time 0. Okay, and so what we're going to do is we're going to be matching those up to the expressions that we have here. Okay, on the right-hand side of Schrodinger's equation, once we integrate it, we've got one term, well, we've got a term that looks like this, h of t psi of t dt. And now here's where it's going to be important that even though I should put an I here, or I can put an I there. So here's the point is that even though that h of I might be very complicated, the fact that it's only lasting for a very short time means I can approximate it by just what its value is near time t equals 0. So I can just write this by multiplying delta by hi 0 times psi of 0. Okay, and then the only reason we can do that is because delta is supposed to be very small. Okay, so now if we take that, we can solve for psi of delta. Namely, it's 1 minus I delta over h bar, hi. Now, since hi is only evaluated at 0 here, I'm not going to bother with the time dependence anymore. Okay, so we've solved for that. And now we can go ahead and plug in this and this. So let's do that. So on the left side, we get sum over m prime, b m prime, m prime. On the right, we get 1 minus I delta over h bar, the interaction Hamiltonian, sum over n Bn n. Okay, and then there were these factors here, but what we've done is we've cleverly arranged that when we plug in delta here, this just equals 0, so I'm taking e to the 0, which is 1. And on the left side, when I plug in t equals 0, this is just turning into 1. And so the exponentials just go away, and that's why I didn't write any exponentials here. Okay, now what are we going to do with that equation? Now we're going to use orthonormality. And so we're going to multiply both sides by the bra k prime and use orthonormality. So we're assuming here that when we chose our eigenstates of h0 and h0 prime, well, specifically h0 prime at this juncture, we chose them to be orthonormal, and we have a theorem that says we can always do that. Okay, and so what have we got? We've got sum over m prime. Bm prime is just a number. K prime m prime equals sum over n Bn times the quantity k prime n minus I delta over h bar. And then we have a matrix element k prime hi n. All right, now on the left-hand side, something nice happens because of orthonormality. That's just a Kronecker delta of k prime and m prime by orthonormality. That means when we sum over all m prime, we're only going to get one term in the sum that survives, namely the one where m prime is equal to k prime. And so the whole sum just amounts to b of k prime. And the reason that's good is because if you think about it, what do we want to know? We want to know what the final state will be. And so what we really want to know is we want to know what are these coefficients, bm prime, and we've just solved for them because here we have b of k prime equals whatever this is on the right-hand side. And now we can just relabel k prime to m prime if we want. Okay, so relabel k prime as m prime. And the end result is bm prime equals a sum over n. Our initial coefficients, b sub n, times something that I'm going to call a sub n to m prime. That quantity is just all of this stuff in the square brackets. Okay, and so where I've defined a of n goes to m prime to be m prime n, that matrix element, minus I delta over h bar, m prime, my complicated Hamiltonian in the middle, times n. Okay, and so that's the solution to the sudden approximation. And so let's review what it says. It says we start off with some initial state. And if we know the initial state, that means we know the coefficients b sub n. Okay, so we know those. Then we compute this quantity a. Okay, and we compute it because we know everything involved on the right-hand side. We know the stationary states for h0 and h0 prime. So we know this and we know this because we know we're given the interaction Hamiltonian. And then we sum over all of those, and that gives us the coefficients in the final state, which is what we'd like to know. Usually you start with some state you know, and you want to know what the state is going to be later. Okay, and so that stuff in the box is basically the solution to the sudden approximation. Okay, and these are given names. So this A sub n n prime is known as a transition amplitude in general, not just in this example. In this example of the sudden approximation, that's what it equals.
What's with this N you said is the transition amplitude? The
I'm sorry, I
N?
couldn't hear that. What was that?
The N, you mentioned the N is the transition amplitude?
No, the whole A sub n m prime is what's the
Okay.
transition amplitude. Okay. And so this expression on the right is what we got in the sudden approximation. We are going to return probably next week, early next week, we will discover what's the transition amplitude more generally when we're not making just the sudden approximation, but in time-dependent perturbation theory. And then what we'll find out is that it matches this within some approximation. Okay. All right. So in fact, there are two special cases of interest, one of which will be especially interesting for the homework. And we'll do examples of that one. So let me say what the two special cases of interest are. One is I could have a situation where H0 prime and H0 are the same thing. In other words, I have a simple Hamiltonian, some weird perturbation happens in the middle or some complicated thing happens in the middle, and then it goes back to the Hamiltonian it started with. And in that case, the matrix element M prime n in the transition amplitude, that first term in the transition amplitude, is just going to be 0 for M prime not equal to n. Because they're the same Hamiltonian, I can give them the same stationary states, and then orthonormality holds. And so if I'm asking what is the amplitude, the transition amplitude to go to a different state, it's just going to be 0 that is the contribution from that first term. And so everything comes from the second term. Okay, and so if I ask what's the probability for, in this situation, for n to go to m prime, that's the square of the transition amplitude. And so since I'm able to ignore the first term when m prime and n are different, that's going to go like delta squared over h bar squared times the square of the matrix element. Okay, so one interesting thing is that it goes quadratically with the short amount of time that my perturbation is acting for. And so that's, again, this is, we will prove this more generally. As a special limit of time-dependent perturbation theory. And that will happen next week sometime. Okay, but the other special case of interest, which will be on a homework problem that will appear later today and be due a week from tomorrow. This is called the very sudden approximation. Actually, in many books, the thing that I've called the sudden approximation doesn't have a particular name. And the thing I'm calling the very sudden approximation is what they call the sudden approximation. So you have to watch out for that. The very sudden approximation is when delta is just taken to be 0. And so if we go back up to our boxed formula, that means we just get to completely ignore the second term, not the first term. So this is going to be important when the two Hamiltonians H0 and H0 prime are different things, not the same. And then everything is just given by the first term. Okay, so there is, in this situation, no second term. And so in particular, this is very common. You might be in an eigenstate of H0. So if we are originally at time t less than 0 in an H0 eigenstate, okay, so one of the BNs is 0, or sorry, one of the BNs is non-zero. In fact, one of the BNs will be just 1, and all the others will be 0. Okay, then in the final state, the coefficient Bm prime is just going to be the matrix element m prime with n. And so if I ask for what's the probability to find yourself in the state m prime after starting in the state n, that's given by the square of the transition amplitude. And so what we found is that that is just m prime n squared. So if you think about it, it couldn't possibly have been anything else. If delta really is so small that it doesn't matter, then it doesn't matter what the H interaction is, right? And so the only thing that could possibly make a difference is what's my initial state and what's my final state. And given two states, what are you going to do to get a probability? You're going to take the square of the matrix element. That's about the only thing you could possibly do. Okay, so that very sudden approximation is hopefully pretty straightforward. Okay, so now we're going to do a couple of examples. And I guess I don't have time to really finish the example, so I'll just set them up. So I'll do example 1 here. So suppose you have a harmonic oscillator, and we'll just take it to be a one-dimensional harmonic oscillator, and suddenly some demon decides to double the spring constant or something like that. So the spring constant of a harmonic oscillator, actually I'll say the natural frequency changes so that the natural frequency goes from omega to 2 omega. And then you can ask, given that happening very suddenly, what's the probability of remaining in the ground state? So the key thing to realize when you're attacking a problem like this is that what does it mean to remain in the ground state? The wording is a little bit tricky because the ground state is changing. The ground state before you change the frequency is different from the ground state after you change the frequency. So ground state before should be labeled slightly differently. I'm going to call it 0 for ground state sub omega, and the ground state after I'm going to call 0 2 omega. So the key thing is it's a different state. One of them is playing the role of what we called n. The second one is playing the role of what we called m prime. Okay, and so our probability of remaining in the ground state is the probability of going from the omega ground state to the 2 omega ground state is this matrix element squared. Okay, so we are out of time for today, but next time what we will do is evaluate that thing numerically, and then we'll do a slightly more practical problem involving tritium decay. which is a classic example of the sudden approximation. And we'll explain why tritium decay obeys the sudden approximation. And then we'll continue on with generalizing things to time-dependent perturbation theory. Okay, that's it for today. Are there any questions on today's lecture? All right, then if not, I will see you all on Friday.
Professor?